Hello everybody, and welcome to our first online video. We're going to start by reviewing. If you turn to page 95 in your book, you'll probably already have this filled out, but the electron configuration for carbon was 1s2, 2s2, and 2p2. And we know that from the periodic table. 1s1, 2, 2s2, 2p2. And then this question is asking, identify the valence shell and the number of valence electrons. So the valence is anything that's in the most recent row. So anything past the last noble gas that you passed. So carbon is here. So we passed a noble gas here, and that was the 1s2. So that's our core, and the rest is valence. So this was core, and then this part is valence. And then we could do a similar thing for scandium, and scandium 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then the D's are one behind, 3d1. So if I write all that out, if I use the shorthand notation, that would be argon for my core. So I have an argon core. And then in the valence, I've got 4s2, 3d1. And sometimes some books will write these in numerical order, and sometimes they'll write them in order that they're filled. Either way is acceptable. All right. Now this is important to understand what's core and what's valence, because all the chemistry happens in the valence. And so whether you gain or lose electrons depends on how many valence electrons you have. So for example, group 1 have one valence electron. So group 1, remember, is this first column. So we just passed a noble gas. So then we've got one valence electron in this first column. And that's why they make a +1 charge. So for example, if we look at lithium, the core is helium, and then you have 1s1. Well, it's easy to lose just one electron. So that's why group 1 is +1. And that's true for all of these ones in the first column, because you just passed a noble gas. So you just have 1 in the valence, then 2 in the valence, and so on. So you can lose both of those in the valence in the second column, or all 3 in the third column. And then you have kind of the opposite phenomenon happening when you get close to the noble gas. So you can gain 1 electron to get a complete shell, to get a core, and a core is stable. So in the first column you can gain 1, in the second column you can gain 2, in the third column you could gain 3. So electrons are negative, of course, so -1, -2, -3. Once you get towards the middle, then the atom you could think of being kind of torn. Do I lose 4? That's a lot to lose. Or do I gain 4? That's a lot to gain. And in fact, it's hard to do because like charges repel each other. So if, for example, I'm gaining, I'm building up this negative charge on the ion, and it doesn't really want to attract another electron. All right, so that was just a quick review. Now let's apply it to new stuff. So on the next page, in forming ions, an atom's core, so that's that thing that's in brackets, that last noble gas that you pass, does not change. So the chemistry doesn't happen there. It's convenient, therefore, to use a model and notation that focuses only on the valence that do change when ionization occurs, and this is called Lewis dot symbols. We'll use this notation when we theorize how atoms bond together chemically. So now let's think about how oxygen and sodium could ionize to form stable ions. So oxygen, we'll just write down an O for oxygen, and we know that it's 2 away from having a complete shell. If we write out the electron configuration, it's helium 1s2, sorry, helium is the 1s2, helium 2s2, 2p4, right? 2s1, 2, 2p1, 2, 3, 4. Okay, so this is our valence. Now, if we want to make a stable ion, we just would need to add 2 more, and then we'd be at the neon core. So far I have 1, 2, 3, 4, 5, 6 in the valence. The way we show that is with dots. So the helium core is just assumed, and then we put 6 dots, and that would be neutral oxygen. And then if we wanted to make a stable ion, then we would add 2 more dots. So this is neutral oxygen, and then if we add 2 more dots, then that will have a charge of -2, and that will be stable, and it will be essentially equivalent to a neon core, right? And then we could do the opposite kind of thing with sodium. So sodium is here, you have a neon core, and then a 3s1. So neon core, 3s1. So neutral sodium has just 1 dot because you only have 1 electron in the valence. So how would you make a stable ion? You would just lose that 1 dot, and then you're left with the neon core. So Na plus with no dots. That's it. And then that is also stable, relatively stable, and that's equal to the neon core. Alright, so then draw a complete electron dot symbol longhand for the compound form. So if you think about what happened here is we gained 2 electrons. And what we had here is we lost 1 electron. So now how could we make a compound? Well, if you think about, here's a neutral oxygen again. And I'm going to draw the dots in a little bit of a different position just because I have some foresight about what's about to happen. So this is still 6, right? It's just like the neutral oxygen I have up here. It wants to gain 2. Well, I have a sodium over here. It wants to lose 1. Sorry, sodium. And I have a sodium over here. It wants to lose 1. So how could I make a compound where these 2 sodiums could lose 1 and the oxygen gains 2? Oh, they can cooperate this way. So this sodium electron can go there, this sodium electron can go there, and overall, if these are my reactants, and the oxygen gains 2 electrons and each sodium loses 1, then you end up with Na with no dots plus O with 8 dots, 8 electrons in the valence, -2, and Na plus with no dots, and you're all set. That's the compound. 2 Na pluses and O2 minus. This is a compound called sodium oxide, and we know that it's Na2O because that's the only way that you can have a neutral compound overall, where sodium loses its 2 electrons and oxygen gains its 2 electrons. You need 2 sodiums and 1 oxygen for that to work. Alright, see if you can do the rest of this page by yourself, and also then the practice problems, and I'll come back and talk to you in the next video.